Students. I am Professor NAVNEET KAUR from EC Department, SIRT College, Bhopal. Today I will be taking lecture on subject digital communication. The topic which I will be discussing in this lecture is sampling theorem. We already know that sampling is used to convert continuous time signal into discrete time signal. So sampling theorem defines the sampling frequency and the sampling interval when we are doing sampling of the continuous time signal. So according to sampling theorem, there are two statements. A band limited signal having no frequency components higher than FM Hertz is completely described by sample values at uniform intervals less than or equal to 1/2 FM seconds apart. Similarly, in frequency domain, a statement can be written as a band limited signal having no frequency components higher than FM Hertz may be completely recovered from the knowledge of its samples taken at the rate of at least 2 FM samples per second. Now, to start with the proof of this theorem, now we will consider first the message signal FT. FT is a continuous time message signal and it is band limited to frequency FM. So when we draw its frequency spectrum by taking its Fourier transform, we will see here the frequency spectrum is represented by F omega. Here the maximum frequency component is omega m. Now to do the sampling of this continuous time signal, we will multiply the message signal Ft by train of impulses delta Tt. This train of impulses is a periodic signal which is having a periodic time period of capital T. When we find the Fourier transform to plot its frequency spectrum, we already know that the Fourier transform of Dirac-Comme function is itself. So when we find the Fourier transform of this train of impulses, we will get train of impulses in frequency domain also with an interval of omega naught between each impulse. So we represent the Fourier transform of delta Tt as omega naught delta omega naught omega. That means that an interval between the impulses is omega naught and the amplitude of each impulse is omega naught. Now, to do the sampling, we will do the multiplication of the message signal and the train of impulses in time domain. Now, when Ft is multiplied by delta Tt, we will get Fst, that is our sample signal. So here we can see that we get impulses, but here now the amplitude of impulses is no longer constant, but it varies with the amplitude of the message signal. So we can say that we have taken samples of the message signal Ft at an interval of capital T. Now to find the spectrum of the sample signal Fst, we need to find the Fourier transform of the product Ft delta T. So now in subsequent slides, we will see how we can find the Fourier transform of Ftn into delta Tt. Now, we know Fst is given by Ft into delta Tt. We are already familiar with the frequency convolution theorem. We know that when the two time-dependent signals are getting multiplied in time domain, then in frequency domain, their Fourier transforms are convolved. So Fst, which is given as the product of Ft and delta T, the Fourier transform of Fst will be 1/2 pi f omega in convolution with omega naught delta omega naught omega, where f omega is the Fourier transform of Ft and delta omega naught omega is Fourier transform of delta Tt. Now, since omega naught is a constant value, we will take it outside of the convolution. So we will get omega naught upon 2 pi. We know omega naught is given by 2 pi by t. So omega naught by 2 pi will give us 1/t. So substituting 1/t in place of omega naught upon 2 pi, we'll be left with 1/t f omega in convolution with delta omega naught omega. Now we know delta omega naught omega is a train of impulses with an interval of omega naught between the two impulses. So we can represent delta omega naught omega, which is a periodic function, as sum of impulses, where delta omega is an impulse located at omega is equal to 0. Delta omega minus omega naught is an impulse which is located at omega is equal to omega naught. Similarly, we will have impulses at omega is equal to 2 omega naught, omega is equal to 3 omega naught, and so on. And likewise, we will have impulses on negative side of the frequency also. So delta omega plus omega naught, which represents an impulse which is shifted at omega is equal to minus omega naught, and so on. So in generalized form, we will write delta omega naught omega as summation m is equal to minus infinity to infinity delta omega minus m omega naught, where m is an integer and it is having value minus infinity to plus infinity. Now, if I'll put m is equal to 0, I'll get first term delta omega. Now, if I'll put m is equal to 1, I'll get second term delta omega minus omega naught. Similarly, if I'll put m is equal to minus 1, then I'll get delta omega plus omega naught. So in generalized form, we can represent delta omega naught omega as this summation. Now, putting this value of delta omega naught omega in our previous equation, which is FST having Fourier transform 1 upon T f omega in convolution with delta omega naught omega. So we will substitute the value of delta omega naught omega here. So now we will have 1 upon T f omega in convolution with summation delta omega minus m omega naught. Now, since f omega is also a function of frequency, so we will take it inside the summation sign. So summation 1 upon T f omega in convolution with delta omega minus m omega naught. Now, by using sampling property of a delta function, we know that if we will take convolution of any signal with the shifted impulse signal, then we will get the shifted signal only. So 1 upon T summation m is equal to minus infinity to infinity f omega minus m omega naught, which represents a shifted signal. So we will get f omega, which will repeat every omega naught radians per second. So the basic representation of f omega, which we have already seen here, it is a spectrum which is varying from minus omega m to plus omega m. Now, if we'll shift it every omega naught, then this spectrum will repeat every omega naught radians per second. So the resulting spectrum, we can see that the basic spectrum of f omega is getting repeated after every omega naught radians per second. Now we can see that the amplitude of T spectrum is 1 upon T. So here we can see in the spectrum that the maximum amplitude of the spectrum is 1 upon T. So we will get a repeated basic spectrum of f omega after every omega naught radians per second. Now, if we want to recover our basic message signal, which is between minus omega m to plus omega m, then we will use low pass filter, which is having cutoff frequency of plus minus omega m. So in that way, we will get the basic message signal, which is band limited to plus minus omega m. Now, it is necessary that if we want to recover faithfully this message signal, then these two neighboring spectrums should not overlap with each other. Because if these spectrum will overlap with each other, there will be overlapping of data and hence there will be an information loss. So for the condition that these two spectrums, these two neighboring spectrums should not overlap, then in that case, the frequency range from 0 to omega naught should be greater than or at least equal to 2 omega m, because the frequency range from 0 to omega m is omega naught. Similarly, this frequency range is also omega m. So in order to recover the message signal, it is necessary that omega naught should be greater than or equal to 2 omega m. So this is the condition which we have derived, that f omega will repeat periodically without overlapping when omega naught is greater than or equal to 2 omega m. Now omega naught is written as 2 pi by t, greater than equal to 2 omega m is written as 2 pi fm. 2 pi will get cancelled. We will get 1 upon t greater than equal to 2 fm, or t is less than equal to 1 upon 2 fm seconds. Similarly, if I write this omega naught and omega m in terms of frequency f, then f naught will be greater than equal to 2 fm. So now I have proved both the frequency domain and the time domain statement, which is t less than equal to 1 upon 2 fm second, and f naught should be greater than equal to 2 fm samples per second. Now we have already seen that if we want to recover our message signal, then f naught should be greater than equal to 2 fm samples per second. This maximum sampling interval, which is t is equal to 1 upon 2 fm second, is known as Nyquist interval. Similarly, the minimum sampling frequency, which is f naught equal to 2 fm samples per second, is known as Nyquist rate. Now, we will see the condition when the signal is sampled at the rate lower than Nyquist rate, that is, when f naught is less than 2 fm. Now, in that case, the neighboring spectrums will overlap with each other, which is shown in this figure. Now, here we can see that f naught is less than 2 fm. Now, in that case, we will get the overlapping of the spectrum and there is an information loss. This phenomenon is known as aliasing. In aliasing, the higher frequency component, that means the higher frequency tail of this spectrum, overlaps with the lower frequency tail of the neighboring spectrum. So in that case, the data will be corrupted. So aliasing is a high frequency component in the spectrum of a signal which takes the identity of a lower frequency in the spectrum of its sample version. Now, when we have already sampled our continuous time signal, in that case, now we can define pulse modulation system. In pulse modulation system, we do the sampling by multiplying the message signal with the train of pulses. In that case, we will get the pulses at an interval of Ts, which is sampling interval, but here the amplitude of these pulses varies according to the message signal. Now, this pulse modulation system is of two types: pulse amplitude modulation, which is known as PAM, and pulse time modulation. This pulse time modulation is further classified as pulse width modulation and pulse position modulation. In pulse width modulation, the amplitude remains constant. The amplitude of the pulses remains constant, but only the width of the pulses varies according to the message signal. So here we can see that as the amplitude of the message signal increases, the width of the pulses also increases. And when there is a decay in the amplitude of the message signal, the width of the pulses also reduces. Similarly, in pulse position modulation, the position of the pulses changes, but width and the amplitude remains constant. So here we can see when the amplitude of the message signal is 0, the pulse is at its reference position. But as the amplitude of the message signal goes on increasing, the position of the pulses changes. It goes towards the left side of the reference position. Similarly, when message signal moves towards the negative side, the position of the pulse, it shifts towards the opposite side, which is towards the right side of the pulses. So here we can see that there is no change in the width and the amplitude of the pulse, only the position of the pulse changes according to the message signal. Now, this is all for today's lecture. Thank you.